Hello everyone, my name is Ashwin Panikar. I'm a Master in Electrical Engineering student at NC State. I'm here to talk about my ECE592 LTN 5G communication project. The name of the project is USRP Power Measurement and RF Front-End Design. Before digging deep into the project, let me talk a bit about RF Front-End and USRP. RF Front-End is generally defined as everything between antenna and the digital baseband system. So this includes filters, amplifiers, mixers, and local oscillators. So you can see a typical diagram of an RF receiver here, and the parts colored in red are the RF front end. So RF front end is one of the most important parts of a transmitter and receiver. This is because it sets the stage for what digital bit error rate performance is possible at final detection. So if you have a very bad amplifier or filter, your bit error rate will be bad in the receiver. So amplifiers also affect the PAPR of your transmitted signal. So RF front end is one of the most important parts in a transmitter or receiver. So let me talk a little bit about USRPs. USRPs are Universal Software Radio Peripheral. It's a range of software-defined radios designed and sold by Etis Research. It's a National Instruments company. So this is similar to RTL-SDR, which I think you might be familiar with, but it comes with higher capabilities and higher cost. USRPs are able to transmit unlike RTL-SDRs, and the receiver bandwidth is also higher compared to RTL-SDR. Multiple USRP models are available depending on the need. Some of the models are X310, N310, B205 Mini, B210. So on the right side, you can see an image of USRP B205 Mini I. It has one TX port, that is transmitter port, one receiver port. And it's one of the smallest USRPs available, and it can be placed in very small areas. So USRPs mainly consist of an FPGA and an RFIC chip. The RFIC chip consists of ADC, DAC, filters, amplifiers, and oscillators. So if you look into the figure given, you can see that the FPGA is connected to an analog device's AD9364 RFIC chip. So the digital signal coming from the FPGA is converted to analog using a DAC, and the signal is then filtered and amplified before transmitting it. So the amplifier might have tunable gain in many of the chips. In case of AD9364 also, there is a tunable RTX gain. This means that the gain of the amplifier can be changed according to our needs. It can vary from 0 dB to 89 dB. So the issue with the output from FPGA is that it has very low power. So the low power cannot be transmitted since the receiver might not be able to receive such a low power. So that's why we use an amplifier. The bandpass filter is used so that it does not emit any spurious emissions outside the frequency range it is supposed to operate. So the frequency range that B205 supports is 70 MHz to 6 GHz. So there will be bandpass filter according to those frequency ranges. Although USRPs are great devices, the USRP front end is not ideal for specific applications. Let me talk a little bit more about why it's not ideal for specific applications. So if you want to transmit a signal from USRP at 1 GHz, there will be harmonics transmitted. The harmonics transmitted will be at 2 GHz, 3 GHz, and so on. So if the transmitted harmonics are at higher powers, it can cause interference with other devices such as mobile phones, Wi-Fi, radars, etc. This interference is not desirable and should be avoided. Another problem is that LTE uses OFDM signals, in which PAPR can be an issue. So the PAPR must be ready so that the signal can be decoded correctly in the receiver. So the signal should not be transmitted at maximum power so that PAP can be avoided. The maximum power that can be transmitted should be known before sending it. Another reason is that USRP receiver receives signals in its entire operational frequency range. For B205, the entire operational frequency range is from 70 MHz to 6 GHz. So this can cause issues with SNR. Therefore, additional front-end designs are necessary for specific designs. There are three major objectives of the project. First is to measure the power of the USRP output. This is done with the help of GNU Radio and SRS-LT. After that, various RF front-end designs are studied and integrated into USRP depending on the power and bandwidth needs. So for the first set of power measurements, GNU Radio was used. GNU Radio is a free and open source software development toolkit that provides signal processing blocks to implement software radios. It works in Linux environment. We can create flow graph as shown in figure for our needs. There are multiple components available to create the flow graph. More details can be found in wiki.gnuradio.org. GNU Radio was used for the measurement of power of square waves. Signal from USRP was generated using GNU flow graph, and the power was measured using a keysight power meter. The figure shows the results of power measurement of a square wave signal using GNU Radio. The figure shows the transmitted power versus frequency for different gain settings. Gain is the amplification provided by the RF front-end amplifier. The gain was varied from 40 dB to 89.8 dB. The frequency was changed from 100 MHz to 6 GHz in steps of 100 MHz. The variation in TX gain was made through the GNU flow graph. Maximum transmitted power was measured to be around 18 dBm for a gain of 89.8 dB at 100 MHz as seen from the plot. We can see that the transmitted power decreases as frequency increases. The transmitted power is directly proportional to the gain value, except at high gain where it saturates to around 18 dBm. Let me talk about two other tools that were used to measure the power in an OFDM signal. One of them is SRS-LT. SRS-LT is a Linux-based free and open source LT software suite developed by Software Radio Systems. With SRS-LT, one device or USRP can act as the user equipment and the other as ENB and APC. The two devices are then connected and experiments can be done using that. Downloading and using SRS-LT is very easy, and if any of you are interested, you can use the following link to download and use SRS-LT. The next tool that was used is iPerf. iPerf is a widely used tool for network performance measurement and tuning. It is significant as a cross-platform tool that can produce standardized performance measurements for any network. iPerf has a client and server functionality and create data streams to measure the throughput between two ends in one or both directions. The data streams can be either transmitted TCP or UDP. There are two versions of iPerf available, iPerf 2 and iPerf 3. I have used iPerf 2 for the measurements. So let me talk more about the test bench that was used to measure the power. So you can see that there are two USRP controllers used for controlling the two USRPs. One will act as the UE and the other as E node B. The two USRPs are connected to the controller as well as to each other. One USRP is connected to the oscilloscope as shown in figure. So the USRP is connected to the oscilloscope through a direction coupler. One end of the direction coupler is connected to the oscilloscope and the other is connected to the E0B. The transmitter from E0B is connected to the receiver of UE and vice versa. Now the power measurements can be made. So I will talk about how I have made the power measurement in the next slide. Let me talk more about the testing process. The first step to test is to run SRS EPC on machine 1. The next step is to run SRS ENB on the same machine in a different console. SRS UE should be run on a different machine, machine number 2. After running SRS UE, a link between ENB and UE will be established. Control channels will be transmitted between ENB and UE, and the power can be measured. Then you have to start IPEF on both machines and measure the power again. This will have higher power as we are transmitting data now. Repeat the same step for UE. And in this slide you can see the screenshots for starting EPC and ENB in machine 1. The command for starting EPC is sudo srs EPC, and the command for starting ENB is sudo srs ENB. You can see that the downlink and uplink frequencies been defined over here. The downlink frequency is 2685 MHz and uplink frequency is 2565 MHz. Similarly, the command to start SRS UE is sudo srs UE, and you can see that now ENB and UE are connected. You can see that RRC connected and network attach successful shown up. So on the right you can see the result for power measurements when ENB was transmitting with and without IPEF, that is with and without data. So the TX gain was swept from 50 to 89 dB in steps of 5 dB, and you can see that the max TX power increased linearly when ENB was transmitting with IPEF. Different resource blocks were used to measure the power. Resource blocks of 15, 50 and 100 were used. When the ENB was transmitting without IPEF, that is without any data being transmitted, you can see that the transmitted power was less than what it was transmitting with IPEF. The ENB max transmitted power varied linearly with increase in transmitted gain while running IPEF. ENB transmitted power is almost similar for different number of resource blocks for constant TX gain. ENB transmitted power without IPEF is not as linear as with IPEF. Similar measurements were made while USRP was transmitting with IPEF. So the USRP maximum transmitted power varied linearly with increase in transmitted gain. The UE transmitted power was different for different number of resource blocks for a constant TX gain. UE transmit at a frequency of 2565 MHz. So the figure on the right shows the spectrum of UE transmitting at 50 resource block and a TX gain of 50 dB. So the UE transmitted frequency of 2565 MHz. You can see that at 2.565 GHz there's a big spike in the spectrum. That's where the signal is being transmitted. You can see a harmonic at around 5 GHz. That's the second highest signal except the one at DC. So as DC is not counted, harmonics can be the second highest power that is transmitted. You can see multiple spikes everywhere in the signal. This is due to interference from the signals outside and leakages from the SDR. Here's a close-up view of the OFDM spectrum. The bandwidth is 10 MHz and we can see the local oscillator leakage at the center of the spectrum. The figure on the left shows the time domain waveform of the transmitted signal. The figure on the right shows the power measurement of the spectrum using oscilloscope. From the results of power measurements of both square wave signal and OFDM signal, it can be seen that the difference between maximum transmitted power is around 12 dB. This is a PAP headroom needed for transmitting any OFDM signal. That is, if the maximum transmitted power of a square wave is around 20 dBm, OFDM can be transmitted at 12 dB less, that is at around 8 dBm. From these measurements, we can go to the RF front-end design. The RF front-end design can be different according to our requirements. So this is the first RF front-end design. In this design, multiple frequency bands can be used. We can see filters connected to a divider combiner, and then to a power amplifier, and then to a low pass filter. Here it's not capable of MIMO transmissions. There are lots of front-end devices, and it will be a bulky design with higher cost and power consumption. The next design uses only a single frequency band. It's capable of MIMO transmissions, and the number of front-end devices are reduced. You can see that only one filter is there in the transmitter path. The cost and power consumption reduces compared to design option 1. There is no amplifier in TX chain, and that means that the output power will be less compared to the design option 1. These are some of the RF front-end design options available. There are other design options available depending on our requirements, such as the frequency band, the size of the equipment, the cost, etc. So that's it with my presentation. These are the references if anyone wants to get more information about Genie Radio, USRPs, SRSLT, or any RF front-end design. I would like to thank Dr. Oscar Ostemir, Dr. Karthik Vasudeva, and Dr. Michael Batz for their help in my project. So that's the end of the project presentation. So if you have any questions or queries, you can comment below. Thank you.